Okay, this is the same example as I did last lesson. Sorry to repeat examples, it's just these questions are quite hard to come by. I wrote these questions, but it just takes quite a long time to work through them. So, yeah, hence the repetitiveness. So the first thing, we had a small smooth sphere moving with velocity 1.5, rebounds off a smooth wall. That makes the impulse perpendicular to the wall if it's smooth. And then it's travelling with velocity 4.1. And the first thing was find a vector perpendicular to the wall. So this bit hasn't changed. So we know that the impulse is the change in momentum. So it's m lots of 4.1 minus 1.5. Which is equal to 3 minus 4. And we know the impulse acts perpendicularly, so 3 minus 4 is perpendicular to the wall. A couple of you in your homework actually, there was a question a little bit like this on your last homework, just when I'm thinking about it. And yeah, you didn't actually draw your diagrams particularly well, so just think about this with these. So if you've got a vector 1.5, across 1, up 5, a vector 4.1, across 4, up 1, and then you can just check everything's working. So my impulse of 3 minus 4, it looks like 3 minus 4-ish. It's never going to be perfect, but you can just sort of double check your work as well with a good diagram. Right, calculating E. So we're going to use the dot product. So to find the magnitude of this velocity that is acting in this direction, I can dot product with a unit vector travelling in this direction. So the impulse is 3 minus 4. So a vector going this way is going to be minus 3, 4. So what I want to do is I want to do 1.5 dotted with a unit vector travelling in the direction of minus 3, 4. So you need to divide by the modulus. So I'm looking at the square root of 4 squared plus 3 squared, which is 5. And that's now a unit vector direction travelling in this direction. Sorry, I'm not feeling great in my ears today. I'm trying my best. So that's going that way. And so this will give me the magnitude of this vector cos theta. So it's projecting it over. You might want to just pull out that fifth actually. So it's 1/5 lots of minus 3 plus 20, which is equal to 17 over 5. And then doing the same with this vector, but this time they're both travelling out of this angle, so that's fine. So I want to do 4.1 dotted with a unit vector in the direction of the impulse, which is 3 minus 4. And then that's going to give me 1/5 lots of 12 minus 4, which is 8 over 5. And then to calculate E is the separation speed, which is 8 over 5, acting this way from this vector. And then I divide by the approach speed, and that gives you 8 over 17, like so. They're quite a different method. The only other thing I wouldn't mind adding on there is if you want to find a vector of magnitude 17/5 travelling in this direction here, in the direction of -3,4, then you have to do 17/5 times by that unit vector. I'm going to regret this because I don't think I've got a calculator on me. So I have 17/25. And I guess you could just leave it like that, or you could combine it into one. So 17 times 3. And 17 times 4. So that's a vector of magnitude 17/5 travelling in the opposite direction to the impulse.